Hello, my dear friends. We are going to take now the next lecture related with the design of synchronous sequential circuit. That is a part 3. And we are going to design using the Milli model now. Previously, we have used the same problem with the Murray model. Now we are going to study the same sequence detector circuit using Milli model. State definition of the Milli model. Now, in a Milli model, how many states are required? 3 states are required. And I told you that it is a less number of states are required compared to the Murray model. In a Murray model, we had used 4 states. So here it is one less state is required and output is going to be generated 1 clock cycle earlier than Murray model. Since the output can be derived using a state as well as input, we need only 3 different states for 3-bit sequence detector circuit following Murray model. The 3 states are designated state A, state B and state C. Represents none, first bit and second bit is going to be detected. When the circuit is in the state C, if the input is as per the pattern, the output is generated in the state C itself with proper logic combination of the input. Not the difference with the Murray model where output is generated 1 clock cycle later in the state D and also require one additional state. State transition diagram using Milli model. Here, the output is written by the side of the input along the arrow path in the format x oblique y, where x and y represents input and output respectively. Here, the format is slightly different. Here, we are writing the state either A, B and C inside the circle. That means state is going to be represented inside the circle. And the input and output, that is input is going to be the capital X and output is going to be capital Y, that is X oblique capital Y is going to be represented along with the path, along with the arrow it is going to be represented. So this way it is going to be different from Murray model. Remember, in the Murray model the format was inside the circle S oblique Y. S stand for the state and Y stand for the output and the input was along with the path. Figure 11.2b shows the state transition diagram of a given problem following Milli model. The explanation is as follows. You can see that there are 3 states are required. This is one circle which represents one state. This is another circle, state B will be there and there is a state C is going to be there. So that means there are 3 circles are going to be there. When it is in the state A, none of the bit is going to be detected in a sequence detector. So it is initial state we can consider. Now when it is in an initial state, there are 2 possibilities of the input. X can be 0 also, X can be 1 also. If you consider that the input data which is coming on the first clock cycle, that is X is equal to 0, that means none of the bit is going to be detected and it resides into the state A only. So you can see that this arrow is initiated from here and come back to the state A only, which represents that none of the bit is detected and it resides into the state A only. But when it is in a state A and if the input data X is going to be 1, that means the first bit in a sequence is going to be detected and it cannot reside into the state A, but it makes a transition from state A to the state B and its output is going to be remains 0 because total sequence is not detected, only one of the bit is detected, but it will make a transition into the state B now. Now consider that it is in a state B. Again, there are 2 possibilities of the input. That means X can be 0 also, X can be 1 also. If x is going to be 0, what happens? Then again the sequence is going to be broken, and hence it will go to the initial state A. That means it has to start a fresh detection of the sequence, binary sequence, that is 0 1 1. That has to be start again. So from the state B, again it will come back to the state A. So it is represented with this arrow. So if it is in state B and it receives 0, that means the none of the bit in a sequence is going to be detected, and it will recite to the state A and wait for this kind of sequence. But if it is in a state B and it receives the 1, that means it will go from the state B to the state C, because the 2 bit in a sequence 1 1 is detected, and hence it makes a transition from the stable state B to the state C. But still only 2 states are going to be detected, so output Y remains 0. Now when it is in a state C, and again there are 2 possibilities, that x can be 0 also, x can be 1 also. If x is going to be 0, it makes a transition from C to A, and it is having x is going to be 0. So all the 3 bits in a sequence is detected, and output Y is going to be signaling that the 3 bit in a sequence is going to be detected properly, and output Y is going to be high. So that's why output Y is going to be 1 over here. But if it is in a state C and it receives the 1, that means the sequence is going to be 1 1 1, and that means it is still sequence is not detected, but it is possible that if there is a next 0 is going to be there, the sequence can be detected. So it will be recite into the state C only. So if it is 1, it is initiated from the C and terminated into the C, but still it is waiting for the sequence to be detected, so output Y is going to be 0. So this way the state transition diagram of sequence detector circuit using Milli model can be obtained. This is all explanation related with the Milli model. The circuit is initialized with the state A. If it receives input x is equal to 0, it stays at the state A, else it will go to the state B if x is going to be 1. That is signifying first bit is detected properly. In both the cases, output Y is going to be 0, signifying no sequence is going to be detected. At state B, if x is equal to 0, circuit returns to the initial state A. It means no bit in a given order is detected, and if x is equal to 1, goes to the state C, signifying 2 bits in the order are detected. In both the cases, Y is equal to 0. Now, when at the state C, if input receives is 0, then all the 3 bits of the patterns are received properly, and the sequence detection can be signaled through Y is equal to 1. Y is going to be high, which indicates that the binary data 0 1 1 in a sequence is detected. Also, the circuit goes to the initial state A and prepare for the new set of detection. At state C, if x is equal to 1, then sequence receives the data 1 1 1, and arrival of 0 in the next clock can make the detection 0 1 1 possible. So at state C, if x is equal to 1, it is considered as 2 bits 1 1 have been detected properly, and the circuit resides at the state C only. The output at the time is going to be Y is equal to 0, since the sequence is not fully detected. Milli model. Since the Milli model requires 3 states for this problem, we have 6 rows in a state synthesis table, as in each state there can be 2 different inputs, x is going to be 0 and x is going to be 1. So we are having 3 different states, small a, small b and small c, and each state can be assigned a binary value 0 0, 0 1 and 1 0. And we can have in a state synthesis table at least 6 rows will be there, because in each state there are 2 possibilities of the input data, that is x is going to be 0 or x is going to be 1. So there are total number of rows in state synthesis tables are going to be 6. Table 11.2 represents the state synthesis table for millimodel. The method remains the same as Murray model, but we use state transition diagram figure 11.2b corresponding to the millimodel from the section 11.2. How to prepare a state transition diagram, state synthesis table for millimodel. This can be prepared using state transition diagram of millimodel as well as excitation table of JK flip-flop, because we are going to utilize here again the JK flip-flop. It has maximum number of don't care in the excitation table, so circuit becomes hardware count, it is going to be simpler. That is the reason. Again, in a state synthesis table, what are the columns will be there? Present state. That means there are two elements, flip-flops, right? So two flip-flops are going to be there, two elements. We designate the flip-flop B and flip-flop A. Flip-flop B is going to be MSB and flip-flop A is going to be LSB. So B is going to be 0, A is going to be 0, that is the state A. B is going to be 0, A is going to be 1, that is the state B. B is going to be 1 and A is going to be 0, that is going to be the state C. Here we are not going to utilize the state D. So the present state we can designate with Bn, An, and that means if it is in the state A, that means the binary value assigned to the state A is going to be 0, 0. And this state A is written here 2 times. State B is also written here 2 times. You see that. And state C is also written here 2 times. Every time the input can be either 0 or 1, 0 or 1 or 0 or 1. So this way these 3 columns can be prepared. Now consider if it is in a state A and it receives the 0, it will reside into the same state. That means according to that state transition diagram, it remains into the same state, and that state, that means Bn plus 1, An plus 1 is going to be the state A, that is going to be 0, 0 only. But if it is in a state A and receives 1, that means it will go from state A to the state B, and the binary value assigned to the state B is going to be 0, 1. So Bn plus 1, An plus 1 is going to be 0, 1. Similarly, when it is in the state B, again there are 2 possibilities for the x can be 0 or x is going to be 1. If x is going to be 0, it will return to the state A. That means it is assigned the value 0, 0 or state A. If it is in a state B and it receives the 1, then it will go to the state C, which is assigned the value 1, 0. So this is the state C, where binary value for Bn plus 1, An plus 1 is going to be 1, 0. Now, if it is in the state C, it receives the 0. That means complete sequence is going to be detected, and it will going to the state A, right, and start fresh detection, and output is going to be 1 in that case. But if it is in a state C and receives 1, it resides into the same state C, that is 1, 0, and output is going to be 0, because still it is output is total sequence is not detected. So this way the first 5 column is going to be prepared. Now this is the inputs requirement for the flip-flop A and flip-flop B. JB and KB is the input requirement for the flip-flop B, and J and K is the input requirements for the flip-flop A. That is, we can obtain from this excitation table. You can see that if Bn makes a transition, flip-flop B is making a transition from 0 to 0, 0 to Bn plus 1, that means Qn to Qn plus 1. It makes a transition from 0 to 0 here. Then what is the J and K is required? J is equal to 0 and K is equal to X is required. So 0x condition is required for this transition. Similarly, A is making a transition from 0 to 0. Again 0x is required for J and K. That way the first row is going to be prepared. Second row now, Bn is going to be 0, Bn plus 1 is going to be 0. Again it makes a transition from 0 to 0. So 0x is required for the flip-flop B. So JB is going to be 0, KB is going to be 0, and similarly AN is making a transition from 0 to 1. So flip-flop A is making a transition, that means AN to AN plus 1 is from 0 to 1, and 0 to 1, for that 1x is required from the excitation table. So here in a second row, J is going to be 1 and K is going to be x, and that way the second row is going to be prepared. Third row, 0 to 0, again it is going to be 0x is required, and 1 to 0. 1 to 0, that is the third row here, that is x1 is required. So you can see that here it is going to be x1 is here. Similarly, fourth one, 0 to 1, for the flip-flop B, that is Bn to Bn plus 1, 0 to 1. 0 to 1, that means 1x is going to be required here, and for flip-flop A, 1 to 0, and when it makes 1 to 0, it may requires x1. So here you require x1, you can see there. Fourth row is going to be completed. Fifth row, 1 to 0, 1 to 0, x1 is required. 1 to 0, x1 is required. So here x1 is going to be required for the fifth row for flip-flop B. And what is requirement for this one? An is going to be 0 and An plus 1 is also going to be 0. So 0 to 0, that is going to be 0x is going to be required. So fifth row is going to be completed. Similarly, sixth row, 1 to 1, when it makes a transition from 1 to 1, Bn is going to be 1 and Bn plus 1 is also going to be 1. So it makes a transition from 1 to 1. That means x0 is going to be required. So here it is going to be x0. And for flip-flop A, it makes a transition 0 to 0, that means it requires 0x, and this way state transition diagram for millimodal can be prepared. Now, design equation and circuit diagram. From the state synthesis table, we can have a Carnot map, and from the using the Carnot map, we can have sum of product equation for design equations for inputs of the flip-flop, that is J and K and JB and KB in terms of the present outputs, that is AN, BN and present input XN. Sorry. In this section, we discuss how to get the final circuit diagram from the state synthesis table through the design equation. In design equation, we express flip-flop inputs, that is flip-flop inputs are J, K and JB, KB as function of present state, that is AN, BN and XN, and memory values here, that means BN, AN and present input, that is going to be X or XN. This ensures proper transfer of the circuit to the next state. The design equation also gives the output here Y equation in terms of the state variable or memory elements in a Murray model and state variable together with the input in a Milli model. So here there is a difference, remember, output Y, which is a function of present value of the output only of the flip-flop A and B. That means it is a Y is a function of AN and BN only in case of Murray model, but in Milli model it is a function of present output, that is A and BN, as well as input also, that is it is also function of X also. So that way we have to draw the Carnot map for the output here. We normally use the Carnot map techniques to get the simplified form of these relations. Milli model. Using a state synthesis table corresponding to the Milli model, we can fill 6 possible positions in each Carnot map. So actually, if there is a 3 variable Carnot map, how many locations will be there? 8 locations will be there. You have studied actually sum of product method. So if there are 3 variables, here our variables are B and AN, that is the present state of the output of the flip-flop, and the third variable is the input, that is X. X can be 0 or 1 and that's way there are total 3 variables are there, 2 raised to 3, that means 8 locations will be there, 8 fundamental products will be there, or you can say that 8 mean terms will be there, M0 to M7. But we have only 6 rows. So remaining 2 rows, that is the state 6 and 7, where you can put don't cares, because we don't know what will be the input for that one, and that input never occurs. So in corresponding to that value of j and k, you can substitute don't care, and that makes no difference. Location bn an x, that is the state number 6 110, and bn an x, that is state number 7 111, are filled with the don't cares x conditions, as such a combination never occur in the detection circuit if properly initialized. The design equation are obtained from this Carnot map, from which circuit diagram is drawn as shown in the figure 11.5b. Note that in this circuit, output directly uses the input information. Here the state synthesis table I again copy down here, because this Carnot map I can generate using state synthesis diagram immediately. You can see that this is JB and this is going to be KB. So these are the two Carnot map for 3 variables Bn, An and X. They are variables. This variable is having a different combination 0, 0, 0, 1, 1, 1, 1, 0, and this is going to be 0, 1. Same way here 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So using this one, what is this fundamental product? 0, 0, 0, that means M0 location, 0, 0, 1, M1 location, 0, 1, 1, M3 location, no 0, 1, 0, M2 location, this one, and this is going to be 0, 1, 1, M3 location. So 0, 1, 2, 3, 4, 5, 6 and 7, these are the location of the mean terms, remember, and you can substitute from here. For this is going to be 0, 0, 0, 0, 0, 1, 0, 1, 0, that means this is going to be M0, M1, M2, M3, M4 and M5. Corresponding to that, what is JB is required? 0, 0, 0, 1, XX. So M0 is going to be 0, M1 is also going to be 0, M2 is also going to be 0, M3 is going to be 1. If you want to verify, you can go here, M3, that is going to be 0, 1, 1. So this is going to be corresponding to that M3, and for that you require JB is going to be 1. Then 4 and 5, 1, 0, 0, that is going to be 4, and 1, 0, 1, that is going to be 5. Both are going to be don't care. Now this is the location 6, 1, 1, 0 and 1, 1, 1, where this inputs are not going to be occur. This condition is never occur, so you can substitute here X. So that way the Carnot map is prepared for JB. Similarly, it can be prepared for KB also. Here you can see that first 4 are going to be don't care, then 1, 0. So here 1, 2, 3 and 4. First 4 are don't care. Fifth is going to be 1, 6 is going to be 0, 7 and 8, that location you are substitute with the don't care. So that way this Carnot map is prepared for KB. Now simplifying this Carnot map, the variable you can have a pair, quad, octet, etc. So if there is a pair is going to be possible using don't care as a considering treating them 1, and we can have this kind of pair. So the variable which is having 2 different value Bn here, which is having 2 different values 0 and 1, so that Bn is going to be drop out. Remaining 2 variables An, which is going to be 1, so An will be there, and X is also going to be 1, so Xan. So JB is going to be available by taking the product of the 2 inputs X and An. Similarly here there is a octet is going to be possible, considering this all X is going to be 1, this query is going to be possible. So two variables are going to be drop out. So variable bn, which is having a two different value, will be drop out. N is also having two different values, going to be drop out. Remains only one variable x, and x is going to be 0. So x is going to be complemented. So kb is only x bar. Same thing you can obtain for from this one, j 01 xx 00, 01 xx 00, and this two location xx is going to be there. Similarly, for k xx 11 xx, here xx 11 xx, and this two location again it is don't care, xx is going to be substituted. So this way you can prepare a Carnot map for j k. Here again for this pair the variable an is going to be drop out. An is having 0 and 1, so an will be drop out. Bn is going to be 0, so it is complemented, bn bar. X is going to be 1, so x is going to be uncomplemented, so j is equal to capital X bn bar. Here in this one, treating all x to be 1, which is encircling the actual one also, it is preparing octet, and hence this value, all the three variables are going to be drop out, and k is going to be 1 only. You require k input to be high only. Now output, I told you compared to the previous thing Murray models, the output was depend upon bn and en only, but here the output is also depending upon bn, n and x. So with respect to this one, we can substitute m0, m1, m2, etc. This output is going to be this. So when the output is going to be high for the state number 4, 1 0 0, the output is going to be high, otherwise output is going to be low. So 0 0 0 0, so 1 0 0, for this condition only output is going to be 1, otherwise it is going to be low. And for this two position it was substituted 0 0. Now this is your pair is going to be there. Bn is going to be 1 and an is having two different value, so it is going to be drop out. So the equation is going to be bn and x bar, because x is going to be 0, so it is complemented. So y is equal to x bar, bn is the characteristic equation for the output. From this characteristic equations we can prepare a circuit diagrams. We can have a two flip flops, the flip flop A and flip flop B. Flip flop A is having the input j and k, flip flop B is having the input jb and kb. So now what is the conditions required for jb? Xan, jb you require xan. So this is your x input is going to be there, and this is the output of this one is an. Both are going to be combined and ending them, that is the input for jb. So xan is the input for the jb. What is kb is required? Kb is required only x bar. If you see the equations, kb is required only x bar. So this x is going to be inverted through this NOT gate, and this output of the NOT gate is connected as a kb. So that way j and k of the flip flop B is connected. Now similarly, what is j is required? J is equal to x bn bar. So j is equal to, this is bn bar, bn bar is taken here, is one of the input of the AND gate, and this is going to be x. So x bn bar is the input for this one, and output is nothing but x bn bar, that is the j input, and I told you k is required only 1, and the clock is given to both the flip flop simultaneously. You can see that this is JK flip flop, negative edge triggered flip flop, and clock is given both the flip flop. When the clock makes a transition, then the data is going to be loaded to the flip flops. Now what is the output? The equations for the output, if you remember, see here, y is equal to x bar bn. X bar is from here, this is x inverted, that is going to be x bar is one of the input of the AND gate, and this is bn. that will be the output Y is going to be produced. And this way, the circuit diagram can be prepared for sequence detector circuit using millimodel. Thank you very much, friends. This way, your syllabus is over. 100% syllabus is over for this 5th semester, friends.